Hello everyone, welcome to lecture 18. The lecture 18 is about mechanics of soil reinforcement. This is from chapter 17 in the textbook, so you can find out the more details if you're interested in the chapter 17 in the textbook. The learning objectives of this lecture is that we're going to draw some more circles for the reinforced and unreinforced soil. And by drawing this Mohr circle, we can find out the effect of reinforcement in terms of the Mohr circles. And the second is to derive the reinforcement stress for the reinforcement rupture and the slippage. We'll see what the rupture means and the slippage means in a minute. And lastly, to relate the rupture and slippage failure to the internal failure of the reinforcement soil. So then let's move on. First, we're going to talk about the mechanics of soil reinforcement in principle. And people interpret the strength of reinforced soil in terms of the Mohr-Coulomb model, Mohr-Coulomb shear strength criteria. And reinforcement provides additional cohesion to the soil, which is called the external or artificial cohesion, CR. So by adding some cohesion term into the soil property, the people just consider that is reinforced. And the Hausmann and Lee also extended this Mohr-Coulomb interpretation method, or the logic, to cover the failure by rupture and the slippage. So in principle, let's think about the case that we have a retaining wall and that there's a soil mass under a stress sigma 1 and sigma 3. And if the wall moves outward, so then it's called the active state, right? And the soil will experience some expansion, the volume expansion, so the sigma 3 will decrease. So at the rest, in the beginning, before the wall is moving, that the circle will be placed in here, right? And this blue line indicates the shear failure envelope. And as the wall moves towards outward, then this sigma 3 will decrease so that the circle will increase. The size of the circle will increase, and it's going to touch the failure envelope, and then it's called the plastic equilibrium condition for the Rankine lateral pressure theory. Right? But when you install some reinforcement, like a strip bar or a sheet or the soil anchors here, like that, then you can, this reinforced earth can sustain more deformation, so larger deformation. So that means that the sigma 3 can be reduced more, not causing any failure. So sigma 3 can be decreased more, so that the circle will increase more, and the red circle indicates the stress state of the reinforced soil at the failure. So maybe like if we consider that the friction angle of the reinforced soil are the same, then we can draw some line with the same angle like this. And this term is like the strength or the cohesion term that's added by the reinforcement. So this is the basic concept. And like I said, the Mohr-Coulomb analysis for the horizontal reinforcement is basically the same I just showed you. And tangential reinforcement is the most effective in placed in the major principal plane, which is the direction of the minor principal stress. So if the case that sigma 3 is the horizontal stress, like this, then the horizontal direction, that the placement of the reinforcement in the direction of the minor principal stress is the best. It will be the most effective. So horizontal in the active state. And referring to the again, the circle here, C, so circle C, in the previous lecture note, we can draw the line here with the same friction angle phi and the failure criteria of the failure envelope will be labeled as a reinforced soil. So here the cohesion intercept is not 0 anymore. And this is the case where the rupture occurs by the at the reinforcement. So this means that one of the reinforcement or the reinforced strip is broken at some point by the tensile stress. Maybe like it can be just broken here, or it can be broken here, somewhere, anywhere, right? So this is called a rupture. So that you have a strip, maybe like strip, and strip gets broken, right? And it's called a tie break also. And in this case, we know that the coefficient, lateral pressure coefficient Ka is a sigma 3 naught over sigma 1 naught here. So the sigma 3 naught is equal to Ka times sigma 1 naught. So assuming there's no slippage of the reinforcement, which means that the reinforcement is failed by rupture, then for the reinforced soil at failure, we may write the sigma 3f here is Ka times sigma 1 naught minus 2Cr square root of Ka, which is the active pressure from the Lec18 theory. And the Cr is the reinforced or the external cohesion that we just saw before. Here, the external cohesion, which is artificially added by the reinforcement in the soil. And the sigma 3f is sigma 3 naught minus sigma r from this graph here. And sigma naught, 3 naught is Ka times sigma 1. So by inserting this equation into here, something happened here. So the equation becomes this Ka times sigma 1 naught minus sigma r equals Ka times sigma 1 naught minus 2 Cr square root of Ka. So then this term will just cancel out, so that you have this and this only remained. So the equation becomes much simpler. Now the sigma r, so the reinforced stress, is 2 times Cr square root of Ka, or Cr can be expressed in terms of the reinforcement stress and the active coefficient of lateral pressure. And we can express this sigma r in terms of the Kp, the passive coefficient, passive lateral pressure coefficient. So Ka and Kp are defined as follow here: tangent square of 45 minus phi over 2, or 45 plus phi over 2. So Ka is 1 over Kp. Right? So by using this relation, sigma r can be expressed as a function of Cr and the Kp. Right? So also Cr will be sigma r times square root of Kp over 2. Good. So and then let's look at the case where the slippage occurs. So here now it's now about the rupture of the reinforcement. We're assuming that the reinforced strip or bar or the sheet will be just slip and failed by the friction, so frictional failure. So it's a failure by the slippage, and in this case, we have to consider the friction between the soil and the reinforced material. So let's say that this is a reinforced material. Then there will be a normal stress, the vertical effective stress, sigma 1 naught. And the pull out force or the stress that's caused by this normal stress will be mu times sigma 1 naught on normal stress. So here we have to know the coefficient of friction, or the friction coefficient, which is mu or F between soil and reinforcement. Okay, let's compare the slippage failure and the rupture failure here. When the rupture failure occurs, in the case of the reinforced soil, you have this kind of a Mohr circle. So initially, the stress will be like this, and as the wall moves, so that in the active case, it moves to the left side, so the circle gets bigger, so that it's gonna touch the some shear failure envelope for the reinforced soil, and that's we can consider it as a cohesion, addition of the cohesion. But in the case of slippage case, it's not anymore the additional cohesion. It will be more like additional friction. So that here you can see that you have a different line with a different friction angle, which is phi r. So the phi r is much larger than the original phi, which is soil, of the friction angle of the soil. So that the Mohr circle was here initially, and as the wall moves, that you have a more friction developed, so that it's gonna fail at different failure envelope. So the difference between the rupture is that rupture is designed as the additional cohesion, and slippage is designed in terms of the additional friction, so phi r. So from now on, we're gonna see how we can interpret and analyze this phi r effect, the friction effect by the reinforcement in the slippage failure. So recalling the Rankin's active condition, sigma 3 naught, the initial condition of the minor principal stress at the initial condition is Ka times sigma 1 naught. So the Ka here is the 1 minus sine phi over 1 plus sine phi. And Rankin's active condition for the reinforced soil at failure with slippage can be expressed as follows, like sigma 3f equals sigma 3o 3 naught. So like I said again, here, and here. So the difference between sigma 3 naught minus sigma 3 will be the sigma r. So the stress, the reinforcement stress. And here, this can be just expressed with this KAR, which is newly introduced here. And KAR is the active coefficient of the lateral earth pressure for the reinforced soil. And here is 1 minus sine phi r over 1 plus sine phi r. So here it's the phi r, the friction angle for the reinforced soil, has been used for this parameter. And by replacing this sigma 3 naught with the Ka times sigma 1 naught, Ka times sigma 1 naught minus sigma r equals Kar times sigma 1 naught. And here we've seen that by friction, using some friction concept, sigma R will be the friction coefficient times the normal stress by the Coulomb friction law. So normal stress times the friction coefficient will give you the shear resistance at the interface. So in the end, as a result, you have this equation. So KAR, so the active coefficient of lateral pressure of reinforced soil will be expressed as Ka minus F. Right? So the active pressure is decreased by this amount, this F, when you have the same amount of the normal stress. And if you rearrange this equation by inserting, so Ka will be sigma 1 minus sigma phi r over sigma 1 plus sine phi r. So then by rearranging this equation, sine phi r will be 1 plus F minus Ka over 1 minus F plus Ka. Here the F is a friction factor characterizing the reinforcement interaction with the cohesionless soil. So that's basically the friction angle between the reinforcement and the soil. If the F is the same with Ka, that will be the limiting value of F, the case where the phi r is 90 degrees, which is impossible. So the failure occurs by the rupture rather than the slippage in this case, because slippage is so strong. The last case is, so now we've been seeing how you can analyze the effect of reinforcement in terms of the Mohr circle and the Mohr Coulomb parameters. So for the rupture, we'll calculate the CR for the design, and for the slippage, we'll calculate the phi r, the friction angle. So then how can we calculate this? Here, for the rupture case, we don't know what the CR is, or we don't know what the sigma R is. Or in this case too, we don't know what F is and phi R is here. So we'll have to derive from the material property to extract those parameters. So consider one-dimensional expansion for a unit element section below. So let's say that this is a retaining wall, and you have a reinforcement placed vertically at the regular spacing with the delta H. Then when you look at this element, will be like this, right? So that you have a reinforced material here, and sigma 1 is the vertical effective stress, and when there's expansion, sigma r is the reinforced stress or the resisting stress. So this is the reinforcement stress. Acting on this area, on this plane, and against the sigma r, sigma s is resisting it. Right? So the force equilibrium is balanced between the sigma r and the sigma s, and sigma s is the tensile strength of the material. So we're looking at, we're thinking at failure condition. So here the AS is the cross-sectional area of the strip, and delta H and delta B is the vertical and horizontal spacing of this strip, respectively. So at the rupture, by the force equilibrium, sigma r times the whole sectional area, delta B times delta H, equals to the sigma S times AS. So the reinforcement stress is resulted by this tensile strength of the material. So it becomes that, so we can manipulate this equation. The sigma r will be expressed as a function of sigma s and AS and delta B and delta H. So if you know for the rupture, if you know the tensile strength of the material, reinforced material, and area, sectional area, and the spacing, then you can calculate the reinforcement stress. Very simple. And what about the slippage? So here, let's think about the slippage case. So in the case of active failure, that failure can occur with some potential failure along the potential failure surface. Then there will be some friction here resisting for the against the soil slippage. So then this L prime will be the effective length against the failure. So let's think about the let's consider the L prime, this region, and what will be the friction, the shear stress or shear resistance by the strip exerted by the frictional force. Then at the verge of slippage, force balance will give you this equation, sigma r times delta b times delta h this is a reinforcement stress, equal to tau s times L prime times b prime times 2. Okay. So here the b prime is the area, the width of the strip, and the L prime is the effective length. And the reason that we are multiplying by factor of 2 is that because the friction is developed at both faces. So here and at the bottom face, the top face and the bottom face. And tau s is the shear stress resulted by the friction at the interface. So tau s is the sigma 1 times tangent delta. And here delta is the interfacial friction angle or skin friction angle determined from the direct shear test between the stripped reinforcement material and the soil. Between earth and soil. So thereby we can finally we'll have this equation, sigma r equals to the sigma 1 times tangent delta times 2 b prime L prime over delta b times delta h. However, when you think about this tangent delta, and tangent delta is from the direct shear test, so that's the case that these parameters will be determined from the location where failure occurs. But in the practice, full frictional resistance does not develop over the entire effective length. So you'll have always the less than this value. So reinforcement efficiency parameter is introduced, ES. So by multiplying this ES into this equation, it will give you more practical and realistic value about the reinforcement stress, sigma r. And recalling this, sigma r is in the frictional or the slippage failure case, F times sigma 1, the normal stress. So that F, the frictional coefficient, is tangent delta times the geometric value of the strip times the reinforcement efficiency. Here the efficiency will be will range between 0 to 1, and I think that there will be a general value and general suggestion for the ES here. So to wrap up, we've seen that here, let me go back. We've seen for the soil reinforcement, we've seen how the reinforcement is working in terms of the Mohs Coulomb frictional failure envelope. And when the strip is failed by break or the rupture, the cohesion, there's an additional cohesion term added by this reinforcement. And if the reinforcement is failed by slippage, then there will be some additional friction angle, the phi r, and this CR and the phi r can be expressed in terms of the the reinforcement stress sigma r here, and also the phi r is F in terms of F. Then we've seen in the case here in the rupture, sigma r is a function of tensile strength of the strip and some geometric value. And here the frictional factor is function of the interfacial tension and the interfacial friction angle between the reinforcement and the soil, and some geometric parameters and the efficiency parameters.